Good morning everyone, good morning all the students. How are you all? I'm also fine. This is Prema here. This is my channel SciMa Academy, and today I'll be starting up with the science chapter. Okay, so I'll be taking up the structure of atom, which is one of the most important chapters of grade 9 chemistry. And I found that from my students and other students, I found that this chapter is little tough for them. They are finding it little tough to understand. So that's why I chose this chapter to explain it to you. Okay, so take your notebook and your pen, and you can pause the video in between to take up the notes, because I'll be presenting the video, I'll be explaining at the same time. Simultaneously you will be taking up the notes also. This will help you in your exam preparations, okay, as exam is nearing, and you can make notes also out of it. Okay, so don't forget to subscribe to my channel, that is SciMa Academy. I'll be coming up with more videos in front of you. So let's start with the chapter. So this chapter is a structure of atom. Children, you must be knowing that anything in this world, anything what you see around you, like you see a table, chair, your pen, pencil, or anybody in the world, anything in the world is made up of atom, right? So atom is the smallest unit of anything, right? It is the smallest entity present. Okay, so any matter, whether it's a solid or a liquid or a gas, is made of atom. So what makes, so like you have seen so many elements, right? You see so many elements, you must be knowing so many elements around you, like we have oxygen, nitrogen, carbon, hydrogen. So these are all also elements which are made of the smallest unit called atoms. Okay, so now what are these atoms? Now what are these atoms? How are these atoms different? Now atoms of one element, now atoms of carbon element will be different from atom of nitrogen element. So why these are different, and how atoms are, whether they are the smallest unit or they are divisible. Okay, so in the second chapter, that is atoms and molecules, you must have studied about atoms. Okay, the Dalton theory of atom or atomic model, the modern atomic theory. Okay, so Dalton said that atoms are indivisible, but later the modern atomic theory says that atom is divisible into subatomic particles. So how this discovery came through, okay, and what is the outcome of this discovery, we are going to take up. We are going to study whether atom is the smallest unit or atom is made up of smallest subatomic particles or not. Okay, that's what we are going to discuss in this chapter. So let's begin. So about the structure of atom, okay, during the in the end of the 19th century, the scientists faced the problem, or they faced the challenge of revealing the structure of atom. Okay, so as such, how the atom is made, how the atom looks like, and what does an atom consist of. Okay, so based on this, to reveal the structure of atom or to discover many theories, so there were many scientists who actually came up with many theories or many discoveries regarding the structure of atom. So we are going to see that only one by one. There are different discoveries which were made about atom, okay, about the structure of atom. So this chapter begins with that topic. Okay, see, before studying atom, now we know the atom is the smallest unit of anything in the world, any matter in the world, right? So what does atom consist of? See, now how the charged particles were discovered. Now we know that there are charged particles present, right? Right now we know that. But before, how there were simple activities which were done in different experiments. There is a simple activity even you can do at home. You can take a comb and rub it with on your head. Okay, you rub it on your hair. So you see that after that comb, after rubbing with your hair, that comb will be starting attracting the bits of paper. Okay, now why this attraction is happening? So if you see, so you see that this comb, if you rub on hair, okay, it will start attracting. It will start attracting the bits of paper. These are the bits of paper. Okay, now why this attraction is happening? Okay, so the conclusion of this experiment, that rubbing of the comb, okay, with the hair, so produce some charged particles. Okay, produces some charge on the comb as well as on the hair. Okay, that means it results in development of some charges on the two objects on which we rubbed. Okay, the comb and the hair. Because of that charge, this charge on the comb started attracting the paper. Okay, so now where did this charge coming from? So now comb is also an atom, comb is also a matter, right, and it is made up of atom. Even our hair also, anything in the world, anything you see is made up of, is a matter, and it is made up of atom, right? So when this matter, this comb is actually producing some charge, it is acquiring some charge, that means obviously the charge is present in the atom, right? So that's how the conclusion came, that atom is made up of some charged particles. Okay, now what are these charged particles? So slowly these charged particles were discovered by different scientists. Okay, so these charged particles were electrons, protons. Okay, neutron was discovered later. So electron was discovered by J.J. Thomson, okay, in 1900. Okay, this was discovered as subatomic particle with negative charge. Okay, so electron is having negative charge. Okay, and the protons were discovered by E. Goldstein in an experiment. Okay, those experiment explanations you don't have in your syllabus, so I'm not explaining that. So Goldstein discovered canal rays, okay, and which consist of the positively charged protons. So these are protons which are positively charged. Okay, and also about the mass comparison, protons mass was found to be 2000 times that of electrons. So electrons mass is almost negligible, so we consider electron mass as almost negligible. So protons mass is 2000 times of electrons, which is, and also equal and opposite charges. So electron is negative charge and protons are positive charge, so they are equal in number, but their charges are different. Okay, they are having opposite charge. So as you can see here, we have electrons negatively charged, protons positively charged. Neutrons we will study later. Neutron was discovered later. Okay, so the first model of about atom, okay, it was given by Thomson. Okay, that was called Thomson's model of atom, or it is also called Plum pudding model. So Thomson explained that in the Plum pudding model, he said that an atom consists of positively charged sphere. Okay, so this is a positively charged sphere, okay, with electrons embedded in it. So electrons are like this plums, and this positively charged sphere is like pudding. Okay, and electrons are like plum in that. So if you can see this figure also, you can understand the atom is made up of positively charged sphere and electrons embedded within it. Okay, see, you have seen watermelon, right? You eat watermelon. So watermelon, you see the red part you can consider as a positively charged sphere, and the seeds you can see that seeds are embedded in it, right? Seeds are present in it like electrons. Okay, so you can easily relate to it. And also he said that the negative and the positive charges are equal in magnitude. That means the magnitude is equal. Okay, and making the atom electrically neutral. So negative and positive charges are equal in magnitude, but they have opposite charge. So he also said that the atom as a whole is neutral because the number of positive charges and the number of negative charges are equal. So they will neutralize each other, and atom as a whole will look like neutral atom. Okay, so these were the two major points which Thomson gave in his plum pudding model for atom. Okay, so atom consists of positively charged sphere and electrons are embedded within it, and the negative and the positive charges are equal in magnitude. Okay, so it makes the atom electrically neutral. All right, so you can take this also as notes also for your exam preparations. Okay, you can pause the video and you can write down this also. Now there was a revolutionary experiment given by Rutherford. Okay, so Ernest Rutherford, as you can see here, in 1871 to 1937. So he is known as the father of nuclear physics. So he gave an experiment. Okay, he designed an experiment to understand how the electrons are arranged, how the electrons are arranged in an atom, and what does an atom contain. So he was the one who actually discovered nucleus also. So he received also Nobel Prize in chemistry for his work in nuclear structure and radioactivity. Okay, so this is the setup. If you can see here, and this is the setup. What is the experimental setup here? What he used fast moving alpha particles. Now what are alpha particles? Alpha particles are doubly charged, or you can write they are doubly charged with 4 unit of atomic mass. Okay, so alpha particles are doubly charged helium ions. Okay, sorry, they are doubly charged helium ions. Okay, so these alpha particles were actually made to pass through the gold foil. Now why this gold foil is used? Very thin sheet of gold foil is used. Okay, now why gold foil is used? You know that gold is a metal, okay, and it is malleable, right? So malleable means, what is malleability? It is a property of a metal where it can be hammered into thin sheets. Okay, and why we need thin sheets of gold foil? Because when alpha particles are hitting on that, when alpha particles are passing on that, so alpha particles will pass only through few atoms. We don't want it to pass through more atoms, okay, of gold, and for here we prevent the alpha particles getting absorbed also. So that's why we need a very thin sheet of gold foil which will help the alpha particles to pass through without getting absorbed. Okay, so here in this experiment, alpha particles were made to from the source, alpha particles were made to pass through the gold foil. Then what you see, okay, what the detector, this is a detector, what it is detecting, like how the alpha particles, what is the nature of movement of the alpha particles, okay, is seen from this experiment. So the experiment setup was fast moving alpha particles were directed at thin gold foil which is 1000 atoms thick. Okay, now alpha particles are what I told you, they are doubly charged helium ions, okay, and mass of 4 units. Okay, and they have considerably more energy and they show minimal deflection. Okay, so they will not show minimal deflection because they are heavier than the protons, because it's helium, doubly charged helium, so it is little heavier than the protons. So we expect in this result alpha particles were chosen because so that it doesn't show much deflection. That was they thought that it is not going to show much deflection. That's why they selected alpha particles for this experiment. Okay, so now what was the observation? So now if you see, this is an atom, so it is passing through the gold foil. Now gold foil, we have large empty space and here you have electrons here and there. Okay, now alpha particles are positively charged, right? So what was the observation? Most fast moving alpha particles passed straight. They passed straight. If you see here, this is passing straight, here also passing straight, here also passing straight. So most of the alpha particles, if you see, they are passing straight through the gold foil. Okay, and some alpha particles were deflected by small angles. See here, some are deflected by a small angle here, some are deflected by a small angle here, right? So some are deflected with smaller angles, and out of every 12,000 particles rebound. Now what is rebounding now? Rebounding means going straight and taking a turn, 180-degree turn. Okay, that's just coming back. That is called rebounding. So if you see, 1 out of 12,000 particles means very few particles actually took a 180-degree turn. They just rebounded straight back. Okay, so very few rebounded like that, but most of the alpha particles, they just went straight. As you can see here also, if you can see here also, you see many are passing straight, right? Straight. Some went by some angle. Okay, some passed by some angle, right? But some took a rebound. Very few you see that they came back 180 degrees. Okay, so most alpha particles pass through undeflected. That means many have gone straight, many went straight, and some were slightly deflected, and very few were deflected with 180-degree deflection, like they went straight back. Okay, so that was his observation when he conducted this experiment. These were the 3 observations he found. Now what was the result? Now what was the conclusion he drew from this experiment? Was that this is a conclusion part. Okay, the conclusion of his experiment was most of the alpha particles passed through undeflected, proving, now if most of the particles are, so now see, most of the alpha particles are just going straight. Okay, this is the central core of the gold atom. So here most of them are going straight, which what it suggests, if most of the alpha particles are just passing straight without getting any obstruction, that means we can say that atoms are empty. Most of the atom space is empty space. Okay, that was one conclusion. Second conclusion, few deflections indicated positive charge occupies very little space. Okay, so some were deflected. Now some were deflected, only little were deflected, right? So here is what present here, electrons are present. Okay, so some, when the alpha particles are parting, they are deflected by small angles. Okay, so what he concluded from that, the few deflections, the less number of deflections which he saw indicated that the positive charge occupies very little space. That means here positive charges are very less. Okay, because here there is attraction from the negative electrons, right? Because this is positively charged alpha particles, right? So here, because of that, deflection is seen, but which suggests that the positive charges are very less in the empty space. Now where are these positive charge? Now that was the question. And he said also that dense nucleus, 180 degree deflection revealed that all positive charge, so when the 180 degree deflection took place, now here when it is passing here, it is coming back at 180 degrees straight. Okay, so that is the rebound which is happening. So which made him conclude that, you know, the mass of the nucleus, mass of an atom is concentrated, or the positive charge of an atom is concentrated in a very small space. Okay, here at the center only, very small space it occupies. Okay, so he says that the nucleus is dense. This is the nucleus. He was the one who actually discovered nucleus, which is positively charged because of protons. Okay, and he said that the nucleus is very small part of an atom, and rest of the part of the atom is actually empty. So rest part, if you see, electrons are here, and it is most of the part is empty, and the main positive part is actually in the nucleus. So he said that 180 degree deflection revealed all positive charge and mass concentrated in tiny nucleus. So nucleus is very small part of the whole atom. Okay, so what were the key features? Now the key features of the nuclear model was positively charged center. That is, nucleus at the atom center contains nearly all the atomic mass. So the atomic mass is, now I told you that mass of a proton is 2000 times that of electron. So electron's mass is considered as negligible, nil. Okay, so where is the mass of the atom concentrated now? If the protons are present in the nucleus, the whole mass of the atom is concentrated in the nucleus only. Okay, so that was his key feature. Nucleus at the atom center nearly all the atomic mass. So whatever atomic mass is concentrated in the center of the atom, okay, that is in the nucleus. And electron revolution, electrons revolve around the nucleus in circular path. And he also said that electrons, now if you see here, electrons are, he said that electrons are revolving around, so electrons revolve around the nucleus in circular path. So if this is the nucleus, you see here, this is the nucleus with this, which is positively charged, and electrons are revolving around it in a particular way. Okay, it is revolving around the nucleus. That's what he's saying. Okay, that was about the electrons, he said. And size comparison, and he said that nuclear radius is about 10 power 5 times smaller than atomic radius. That means it is very small part of the atom. Okay, nucleus is a very tiny part of an atom. If the atom is so big, nucleus will be very tiny part of the atom. Okay, so these were the key features of nuclear model. This was the conclusion of the experiment. These are the key features. Okay, so these were the experiment conducted by Rutherford, but there was a drawback also. Okay, so as I told you now, Rutherford said that the mass is present in the nucleus, positive charge is here in the nucleus, and electrons are revolving around it. Now what happens when the electrons are revolving around it? Now see, if you see, this is the positive part. Okay, this is the nucleus, right? This is the nucleus, and electrons are revolving around the nucleus. So if you see, so if this is the nucleus, positively charged, and I say electrons are revolving around it, right, in a particular way, it is revolving around it. So what happens now, what was the drawback of Rutherford's model was that, see, when the electron is revolving around the nucleus, because it is revolving, it is in motion, right? So when it is motion, it is having some accelerated motion, right? So when a body is moving in an accelerated motion, it always loses energy, okay? It always radiates energy, okay? So this is the electrons which is moving will radiate some energy, right? Ultimately what will happen, it will lose all the energy and it will fall back onto the nucleus. Okay, so that was a drawback Rutherford could not explain. So Rutherford's model faced a problem, that is any charged particle in circular orbit undergoes acceleration, okay, and it will radiate energy. So when it is radiating energy, what will happen? Revolving electron, as it is moving into the spiral orbit, okay, so what will say? It will lose energy and finally it will fall onto the nucleus. So in that condition, what we can say, that atom is unstable. The atom becomes unstable when the electron is falling back onto the nucleus. As such, we say atom will be unstable, okay. So that was something which Rutherford failed to explain, okay, about how the electrons are revolving around the nucleus, okay. This drawback actually was explained later by Bohr, which we will study in the next atomic structure of atom, okay. Now Bohr solved the drawback which we saw in Rutherford's atomic model, okay. So how Bohr gave his atomic model solving the stability problem, okay. He solved the stability of the atom. Rutherford could not explain the stability part of the atom, right? So here how Bohr atomic model overcome those drawbacks. We will see that. It's very, very important and interesting topic, okay. So please pay attention to it. So Niels Bohr actually, he was a professor of physics, and he said that he told two things, okay. One was about discrete orbits. So only certain special orbits known as discrete orbits, okay, where the electrons are allowed to, where electrons are revolving around the atom. So if you see here, so this is the nucleus which is having the protons. So nucleus is the part which is very small part of the atom where the whole mass of the atom is concentrated because of the protons, okay, because proton is only having mass, okay. So now around it, now if you see, this is one orbit, now this is another orbit, okay. Now why this orbit? This is also called energy levels. These are also called energy levels, these are also called shells, okay. So there are different names given to it. So electrons are actually revolving on this discrete orbit only, okay. This is the first orbit, this is the second orbit, like that you will have third orbit also, then like that orbits will be there. So he said that only certain special orbits, now electrons, some electrons will be present in the first orbit, some electrons will be present in the second orbit, some electrons will be present in the third orbit, and they will not move, they will not shift from that level, okay. They will not shift from that energy level. So they will be rotating, they will be orbiting the nucleus in that orbit only, okay. They will be revolving in that orbit only, okay. And the second thing is, he said no energy radiation. So when they are in their discrete orbit, so if the electron is in this orbit, it's not going to lose any energy, it's not going to radiate any energy. And similarly, if the electrons are in the second shell, in the second level, there also electrons will be revolving in that shell only, but without radiating any energy, okay. So that explains that when the electrons are moving in discrete orbits, they are not radiating any energy. That means there is no instability, there is no instability of the atom. So atom as such will remain stable, okay. So there is no electrons radiating energy, not falling onto the nucleus. So atom as a whole is stable, okay. That's what we need. Atom has to be stable. No one wants to be in a unstable state, right? So we need the atom also to be in a stable state, okay. So this 2 points which were explained by Bohr, actually we till now follow that. We follow the Bohr's atomic model, which says that the electrons revolve around the nucleus in discrete orbits, okay. So there are different shells, now if I say here, so see here, so this is the nucleus, so around it you have electrons. So this is the K shell, first orbit will be K shell, then L shell, then you will have M shell, then you have N shell. Okay, so till N shell only you can study. So K shell is the innermost energy level which is closest to the nucleus. So this is the K shell which will be closest to the nucleus, right? This is called first energy level. Then you have L, that is second energy level. So a second energy level is with little higher energy. So as you're going from, farther from the nucleus, energies also will increase. So this is with low energy, this is little high energy. Then the third shell is M shell. Here, third energy level, again little farther from the nucleus, and last is the N shell, very far from the nucleus with the highest energy shown. So low energy, little high energy, higher energy, and highest energy in the N shell. Okay, so this was the atomic model given by Bohr. So if you compare, see, this is a very good example, this is a very good picture, So here the Thomson said that, okay, in atom you have the proton, which is like, the spread part. Okay, here the protons are like the pudding and electrons are embedded in it like plum. Okay, and Rutherford said that the electrons are the positive part of the atom is very, very small, where whole mass is concentrated, which is the nucleus, and electrons are revolving around it. But Rutherford did not give any explanation about the stability of the atom, because electrons are losing energy. He did not say anything how electrons don't lose energy and what is the path electrons take to revolve around the nucleus. Okay, so the Bohr atomic model only which we study, which we follow, okay, which says that electrons are revolving in discrete orbits which are called energy levels based on their energies, okay, from lower to higher energy levels. All right, if you can see here, so this is the nucleus which is having positively charged protons and neutrons also. Neutrons were later discovered, right? So still I've not told you about neutrons. So nucleus consists of protons and neutrons, and you have the first shell, that is the K shell, electron revolving around it, and the L shell you have. Okay, after that you will have M and N shells also. So electronic configuration. Now what Bohr said, what Bohr gave a rule. He gave a rule, that is 2n square rule. Okay, this is called 2n square rule. Okay, which shows the electronic configuration. That is a rule to show how the electrons are distributed. That is distribution of electrons in discrete orbits. There is a rule which Bohr gave, and we follow that rule to write the electronic configuration, how the electrons are present in the in different energy levels. See, now we have elements. Okay, we have elements from 1 to 20 elements which you have to learn, and we have to know the atomic number of that element. You must have studied in the last chapter. Why I am doing this chapter before is that this chapter you have to understand to learn the electronic configuration of the elements, and then further you will learn about the valencies. Okay, after that only if you go back to the atoms and molecules chapter, you will understand it better by writing the valencies and how to write the formulas of a compound. Okay, so here, so we will study now here the 2n square rule. How do we write the electronic configuration? Now 2n square rule here. Now K shell is what? N is equal to 1. This is the first shell. So here 2n square, n means 1, n is 1, right, in the first shell. So n into 2 into 1 square will be 2. That means K shell has the maximum capacity of holding only 2 electrons. Okay, so if you see L shell, L shell is n is equal to 2. So here it will be 2n square, that is 2 into 2 square will be 8. So now the maximum capacity of the L shell is to hold only 8 electrons. Okay, M shell. Now M shell is n is equal to 3, that is a third shell. Again substitute the value 2 into 3 square. You will get how much? 18 electrons. So M shell is having maximum capacity of holding how many electrons? 18 electrons. Okay, if you go for N shell, n is equal to 4, 2n square, substitute the value of n, that is 4. So we will get 32 electrons. Okay, so this is the electronic distribution. Okay, electron, how they are distributed in different energy levels. So K shell has maximum capacity of holding 2 electrons, L shell has maximum capacity of holding 8 electrons, and M shell has having maximum capacity of holding 18 electrons, and N shell has 32 electrons. Okay, so that was the only thing which was given by Bohr in 2n square rule. Okay, and also there is one more, there are different rules which you have to follow. The maximum number of electrons in the outermost orbit is 8. Okay, so maximum, if the outer orbit, if K and L, there are only 2 orbits, so maximum electrons outermost orbit should have is only 8. Okay, the maximum number of electrons in the outermost orbit is 8. Regarding of the shell capacity, I will give you the electronic configuration, you will understand better, I will explain you that. And the third point he gave was electrons are not accommodated in given shell unless inner shells are completely filled. So you have to fill the K shell with 2 electrons maximum, then only you can go to filling of the next shell. Okay, without filling the previous shell, without filling the inner shell, you cannot fill the outer shell. Okay, that is also the rule which you have to follow. Okay, so this is the main 2n square rule which you have to follow to write the electronic configuration of any element given to you. Okay. So in this video we will study about how to write the electronic configuration of the first 18 elements. Okay, so you have to know the 2n square rule. You can see my last video where I have explained you the 2n square rule as to how to fill the electrons in different energy levels. Okay, so after knowing the 2n square rule, it becomes very easy for you to write the EC and also drawing the orbital structure of the different elements. Okay, so we will start with the first element. See, now first to 18 elements atomic number you have to learn in this order only. Okay, so they are placed in the periodic table in this order, that is first element hydrogen till 18th element argon you have to learn. So the first element hydrogen, so I will be writing, see, I will be writing the elements, okay, their electronic configuration, okay, and the orbital structure, or you can also call it as electronic orbital or electron orbital structure. Okay, so these 3 things I will be telling you. So the first element is hydrogen with atomic number 1. So here now I told you K, L, M and N shells. So maximum capacity holding of K shell is only 2, L shell has maximum holding capacity 8, M shell has 18 and N shell has 32 maximum capacity. Okay, so here since hydrogen is only 1, so 1 electron will come to the first shell only, right? So its atomic structure will be first, only the first energy level will be filled with the 1 electron. Okay, this is the first shell. Okay, coming to the second element, I will write all the elements. Okay, till 8 let us see now. So lithium is 3 atomic number, 4 beryllium, 5 boron, 6 carbon, 7 nitrogen and 8 oxygen. Okay, so here now this is helium 2, so it's 2 electron, the K shell will get filled with 2 electrons and there is no further electron to fill other shell. Okay, now lithium is having 3 electron atomic number, so 2, so K shell is having only maximum capacity of holding 2 electrons, so the remaining one will have to go to the L shell. Similarly beryllium will be 2, 2, boron will be 2, 3, carbon will be 2, 4, nitrogen will be 2, 5, oxygen will be 2, 6. So you see here, until the L gets filled with 8 electron, we can keep filling this L shell. Okay, because L shell is having maximum capacity of holding 8 electrons. So until it gets filled with 8, we can keep filling it. Okay, see now I can fill with 9 is fluorine, so 2, 7, right, 7 plus 2, 9, and the 10th electron is neon with atomic number 10. See here it gets filled with 8 electron. Now after this 8 we can't fill it with 9, we can't write 9 here. Okay, we have to go to the next shell later. Okay, So that's how L shell is having maximum of 8 electrons capacity. So if I draw the orbital structure for here, helium, see all will have, only one. Here we have 2 shells. Okay, now here also we'll have 2 shells. Now here also we'll have 2 shells. Okay, so here when we are filling the electrons, see for here we will fill 2 electrons in the first shell for lithium and 1 electron in the second shell. Here we have 2 electrons in both the shells for beryllium. Here boron, 2 electrons here in the first shell and 1 electron in the third shell. Sorry, 3 electrons in the second shell. Okay, and similarly if you see here for carbon also you can draw 1 second shell. So electrons will be 2 electrons. See, K shell is always 2 electrons. Okay, no more than 2 electrons, and 4 electrons in the second shell. Okay, so like this I think you can write for the remaining also. Try writing the orbital structure of the remaining. Okay, it will be having 2 shells and you have to just fill with the respective electrons given. Okay, now after this, after we have written till 10, now what happens here? This is, you see here now sodium. Now sodium is atomic number 1, so it will be 2, 8, 1. See here, this is K shell, L shell and M shell, right? Now L shell is having maximum capacity of holding 8 electrons. So the remaining, now 8 plus 2 is 10, so this is 11. So remaining 1 electron has to move to the M shell. Okay, so electronic configuration will be 281 and its orbital structure will be, this is the nucleus, first shell, second shell, we have to make 1 more shell. Okay, then we will fill the electrons. 2 electrons in the first K shell, 1, 2, 3, 4, 5, 6, 7, 8. 8 electron in the L shell and only 1 electron in the M shell. So this is how the orbital structure of nucleus will, the atom of sodium will look like. Okay, similarly you can go for magnesium. Magnesium is 12, electronic configuration will be 2, 8, 2. Then you have aluminium, 13, electronic configuration 2, 8, 3. Then silicon, Si, 14, it will be 2, 8, 4. Then we have phosphorus, 15, sulfur, 16, then chlorine, 17 and argon, 18. Okay, so this will be 2, 8, 5, 2, 8, 6, 2, 8, 7, 2, 8, 8, 1. Sorry. Now the argon will be 2, 8, 8. Okay, so argon, see, you see here now this last shell is also filled here with the 8 electrons. Now after this further we cannot proceed because it's 18 atomic number. Okay, so till here children you need to know how to make the atomic orbital structure. I have made for sodium, rest all you can make because all these are having 3 shells only. Okay, you can fill the shells with the number of electrons given. Okay, so hope you understood how to write the electronic configuration and the orbital structure of the elements. So students, the next topic is about the valency. Okay, so you have to study what is a valency, what is the meaning of valency and how do we write, what is the method of writing the valency of any element. Okay, so this valency topic was there in your atoms and molecules chapter also, but you cannot understand that, you have to memorize there the valency, right? So here if you understand how, what is the way we write valency, how can we say that the valency of this element is this, so there is a method to write, right? Okay, so we have to study that only. Okay, that's what I'm going to explain you here. So what is the meaning of valency? First you need to understand what is the meaning of valency. So valency is nothing but, valency is the combining capacity of an element. Okay, so just now which we have studied the EC, right? We have studied the EC. So if I say lithium atomic number 3, its EC was 2 1. Okay, now the outermost shell, you know, the outermost shell either has to be filled with 2 electrons, 2 electrons, that is a K shell. If the K shell is complete with 2 electron, this will be called as a duplet. Okay, or it is filled with 8 electrons. Outer shell is filled with 8 electrons. Okay, which will be called as octet. Okay, so atoms with completely filled outer shell, okay, whether it is filled with 2 electrons or it is filled with 8 electrons. If it is filled with 2 electrons, we call it as duplet, or if it is filled with 8 electrons, we call it as octet. Okay, that time we will say that the atom is stable. Atom is stable, right? That means its valency is 0. Why its valency is 0? Because it doesn't have to gain any electron, it doesn't have to lose electron, right? See, atoms are unstable, they have to attain stability, either they gain electron or they lose electron. Okay, so some atoms are filled, their outermost electron is filled, so they are already stable, they don't have to either lose electron or they don't have to gain electron, so their valency is said to be 0. Suppose if I say, give you an example, helium. Now helium atomic number is 2, so its EC will be what? Electronic configuration will be K shell filled with 2 electrons, right? So this is a very good example of duplet. So helium is having duplet configuration where its outermost shell, here it is having only one shell which is filled with 2 electrons, right? So it is having duplet configuration, and so its valency will be 0. Valency is 0 and it is highly stable. It doesn't have to react to attain stability. Okay, it doesn't have to react to attain stability. It is happy with itself. It is not going to lose any electron. It is not going to gain also any electron. It is happy. Okay, it is stable, right? But if you see lithium, now lithium is 1 electron, only 1 electron in the last shell, right? Now if you see lithium, beryllium, boron, atomic number 3, 4, 5, EC2, 1, 2, 2, 2, 3, right? So here if you see here, the last shell is having 1, 2, 3 electrons. So when the elements are having outer shell electrons 1, 2 or 3, they always lose electrons. Okay, they will always lose electron to become what? To become like helium. So whenever an atom is losing or gaining electron, they want to attain the stable electronic configuration of the nearest noble gas. Now this helium is a noble gas. This is the first noble gas, okay, which is stable gas. It is also called as inert gas. Inert gas, or it is also called noble gas. Okay, now these 3 elements, lithium, beryllium, boron, they try to lose these 1, 2, 3 electrons in order to become like helium. They want to become stable. Nobody wants to be in an unstable state. They want to become stable. Okay, so now lithium, what will happen? Lithium is 2, 1. So it's easy to lose this electron, right? It's easy to lose this electron. Beryllium is 2, 2. It's easy to lose this electron. Now you will ask me that last shell can have 8 electrons also, that is octet. They can attain octet also. So but to attain octet, lithium requires how many electrons? It requires 7 more electrons, and beryllium will require 6 more electrons. That means they require more electrons, right? They are able to lose less electron. So here we have to talk about energy, electronic energy. So here to lose 1 electron, here beryllium to lose 2 electron is much easier. Much less energy is required to lose 1 and 2 electron rather than gaining 7 electron here, gaining 6 electron here. Okay, so they will try to, so the atom always try to have a favorable condition, okay, where they are not losing much energy. So where they are not losing much energy, they will try to go with that path. Okay, so here it's easy to lose 1 electron, easy to lose 2 electron. Boron also easy to lose 3 electrons. Okay, it will not gain 5 electrons because lot of energy is required to gain 5 electrons rather than losing these 3 electrons. So it's easy to lose these 3 electrons rather than gaining 5 electrons to become octet. Okay, so here they lose 1 electron, to here 2 electron, and here 3 electron to become like nearest noble gas, that is helium configuration, that is duplet configuration. Okay, so here they will lose electrons, so they will have positive valency. So whenever an element is losing electron, they will have positive valency. So how much lithium is losing? Now lithium is losing how many electrons? 1 electron, right? So lithium valency will be 1 plus. So whenever element is losing electron, you have to put a charge of plus. Okay, and how many electrons it loses? 1 electron, so it will be 1 plus. Similarly beryllium loses 2 electrons, right? It will lose this 2 electron, so it will be 2 plus. And boron will lose how many electrons? 3 electrons, it will having 3 plus valency. Okay, so like that the valency will be how many electrons they lose to attain the nearest noble gas configuration. Okay, now if you see carbon atomic number is 6, its electronic configuration will be 2 4. So in the carbon, say there are exceptions where the outermost electron is 4, right? In carbon and in silicon also. Okay, carbon and silicon also. In elements like carbon and silicon is 2 8 4, 14 atomic number. Okay, so when the last shell is having 4 electrons, they will neither gain nor lose electrons. Okay, they will combine in a different way, forming different kind of a bond. When you go to higher class, you will study about it. Okay, so after carbon, if you see nitrogen, see nitrogen is 7, this is 8 9, this is 10. So what is the EC here? 2 5, this is 2 6, this is 2 7, this is 2 8. Now if you see here the last shell is having 5 electron, here 6 electron, here 7 electron. But here this is neon noble gas, last shell is filled with 8 electron. It is complete, which shows it is octet. So this is stable. This is stable electronic configuration. It will not lose any electron, it will not gain any electron. Okay, so now when it comes to 5, so now nitrogen is having 5, so it will not lose this 5 electron, it will gain how many electrons? 3 electrons it will gain. Here it will gain, oxygen will gain 2 electrons. Here fluorine will gain 1 electron. Okay, because losing 5 electron, here losing 6 electron, here losing 7 electron will require a lot of energy. Okay, which they don't want to lose so much energy. They will lose much lesser energy. Okay, how they lose lesser energy? By just gaining 1 electron. Here by gaining 3 electrons. Here it has to gain only 2 electrons to become 8. Here fluorine has to gain only 1 electron to become 8. Okay, so here in order to not to lose much energy, here they gain electrons. So whenever the outer shell is having 5, 6 or 7 electrons, they always gain. So gaining electron will have negative valency. Okay, so when I say now nitrogen, so nitrogen valency will be N3 minus because it gained 3 electron. Oxygen valency will be 2 minus, it gained 2 electron. Now fluorine valency, it has gained 1 electron, so it will have valency 1 minus. So whenever an element is losing electron, see here, when they lose electron, they will have positive valency. How many electrons they lose? That much will be the valency with the positive sign. Okay, when they gain electron, you have to write how many electrons they gaining with the negative charge. So this is how we learn the valency here. This is how we can learn. When you know the electronic configuration, you are able to easily write the valency of that particular element. Okay, so like that you can write the valency of other elements also. For sodium also we can write. See, sodium, so this is 281, 282, 283. See, now here they are having 1, 2, 3. So they will lose. So they will lose electron. Okay. So how many electrons it will lose? 1 electron. So sodium charge will be 1 plus. Here magnesium will lose 2 electrons. So magnesium charge will be, valency will be 2 plus, right? And aluminium will lose 3 electrons. So its valency will be 3 plus. So when you know the electronic configuration and you know how much electrons it has on the outermost shell. So if the outermost shell is having 1 or 2 or 3 electrons, they always lose. Okay. So which configuration it will attain to lose? It will attain nearest neon. It is like neon, right? Neon configuration is 2, 8. It will attain neon configuration to become stable. Okay, now here they are unstable because the outermost shell is not complete. When an atom is said to be stable, when their outermost shell is complete. But here outermost shell is incomplete because it is not filled with 8 electrons, right? It is not having either duplet or a octet configuration. So in order to become stable, they will try to lose or gain electrons. Okay. So in silicon also, so silicon I already told you, it is 284. Okay, its valency will neither be negative nor positive. That is a different concept. Phosphorus 15, sulfur 16, chlorine 17, argon 18. So this is 285, this is 286, this is 287, right? And this is 288. Now this is also octet. This is stable because its outermost shell is complete with 8 electrons. So here it is having 5, phosphorus having 5, sulfur having 6 and chlorine having 7. So they will gain electrons. Okay, it's easy to gain here. How many electrons? 2 electrons it will gain. So it will become 2 minus. Sulfur will gain, phosphorus will gain 3 electrons to become 8. 3 minus, sulfur will gain 2 electrons to become 2 minus, and chlorine will gain only 1 electron it has to gain. So it will become 1 minus. Okay. So this is how we write the valency of the elements. So first you should know how to write the electronic configuration, orbital structure. Okay. After that you will be able to write the valency. Okay, so if you don't know the atomic number, if you don't know the electronic configuration, you will not be able to figure out what will be the valency. Okay, so practice this. Okay, you can pause the video, you can go back to the videos and go back to the slides and you will understand. Okay, slowly you sit around, say in your house during the weekends and try to write the atomic number, memorize the atomic number and try to write the EC and the valencies. Okay. So you have to also learn about the discovery of neutrons. Okay, so Chadwick discovered the third subatomic particle, that is neutron. Okay, neutron. Okay, and this neutron will have no charge. It doesn't have any charge, and its mass is equal to the mass of protons. Okay, so neutrons are present in the nucleus. So if we have the nucleus here, so protons and neutrons are present inside the nucleus, except the hydrogen atom, because hydrogen atom atomic number is 1, so it is having only 1 proton. Okay, so 0 neutrons, it will not have any neutrons. Okay, so the mass of atom is therefore sum of protons and neutrons in the nucleus. So whatever mass of the atom is because of the protons plus neutrons. That's why protons and neutrons are also called as nucleons, because they are present inside the nucleus. Okay, and the electron will be revolving around the nucleus. So subatomic particles, we have electrons, protons and neutrons, which is comprising the atom. Proton mass is 2000 times of electron mass, so electron mass is considered as negligible, and proton and neutron have mass of 1 unit. Okay, so both proton and neutrons have the same mass. Now coming to the next topic, that is atomic number, mass number and isotopes and isobars, which you have to learn. Okay, so atomic number we denote it by the letter Z. Okay, it is nothing but the number of protons in the nucleus. How many number of protons are present in the nucleus? Okay, which is the atomic number. Okay, so all the atoms of the element have same atomic number. So whatever atoms in that, suppose carbon is an element, all the atoms of the carbon will have the same atomic number. Okay, that is 6. Hydrogen atomic number is 1. So elements are defined by the number of protons they possess. That is nothing but the atomic number. Okay. Now mass number is sum of protons and neutrons. Okay. So sum of protons plus neutrons makes the mass number in the nucleus. So they are present inside the nucleus. Okay. So mass of an atom is present inside the nucleus. Whatever mass of an atom is actually is concentrated in the nucleus. Okay. Because electron's mass is negligible. Electron doesn't have any mass. So whatever mass of the atom you see is because of the combined mass of protons and neutrons. Okay. So the carbon has suppose 6 protons and 6 neutrons. So its mass will be 12 units. Suppose if you have sodium. Sodium atomic number is 11. So its mass number is 23. So I can find out P plus N is the mass number, right? So I can find out the number of neutrons in this. So protons are 11, mass number is 23. So we can find out 23 minus 11, that is 12. So we can find out the number of neutrons present in sodium. Okay, so this way, if mass number is given to you or atomic number is given to you, we can find out the third entity here. So when you, notation of the atom, how do we represent? So when we write, so this is the symbol of an element and we write the atomic number at the top and mass number here. Okay, so X atomic number we denote by Z and mass number we denote by A. Okay, so this is Z and this is A. So if I have to represent say carbon, I'll write the symbol of the element, I'll write its atomic number 6 and its mass number 12. So this is how we represent any element showing the atomic number and the mass number. Now coming to the next topic, that is isotopes. Okay, so isotopes are the elements having, they are actually the elements having same atomic number. They are same elements basically. They are having the same atomic number but different mass. Okay, the best example you have hydrogen isotope. See, if you see here hydrogen, here this is protium, this is deuterium and this is tritium. Okay, a protium has only one proton, which is having only one proton. That means atomic number is 1 and 0 neutron. Whereas deuterium is having So deuterium is having 1 proton and 1 neutron. And tritium is having 1 proton and 2 neutrons. So if you see here, it's the same element with atomic number 1, that is hydrogen. But what is differing here? Here 0 neutron, here is 1 neutron and here is 2 neutrons. Okay, so here what will be the mass? Mass will be 1 plus 1, that is 2. Here mass will be 1 plus 2, that is 3. And here mass will be 1 plus 0, that is 1. Right? So here if you see, masses are different. Atomic number is the same atomic number 1, 1. But the mass numbers are different. Okay? So such elements, they are atoms of the same element having same atomic number but different masses. So isotopes will have similar chemical properties because they have same atomic number. Okay, but they have different physical properties because they have different mass. Okay, so that's how when we want to find the average, so now the atomic mass of suppose chlorine. Now here they give you example, example of carbon also. Carbon isotopes, you have carbon 12 and 6 and carbon 14 and 6, right? And chlorine also you have 35, 17 and 37, 17. So these are the two isotopes of chlorine. So here if you see, the neutrons will differ. So when you see the isotopes, they have different neutrons. The protons will be same but neutrons will differ. Here you can see carbon is having 6 neutron, 8 neutron here. And here chlorine 35 has 80 neutron and chlorine 37 has 20 neutrons. Okay, so when you have isotopes, their atomic mass cannot be a single number, right? Now atomic mass we can't consider as 35 or atomic mass we can't consider as 37 because in nature they are present as different percentage in nature. So if you see chlorine, they are present in the ratio 3:1. Okay, chlorine 35 and chlorine 37. So in the nature, they are present, the isotopes are present in the ratio 3:1, that is 75% and this is 25%. Okay, so how do we find the atomic mass? So here what we have to do is we have to find the average atomic mass. Okay, average atomic mass we find in case of isotopes. Okay, so but if there is a normal element, suppose carbon, you can say suppose sodium. Okay, now sodium atomic mass will be equal to the number of protons or neutrons. Okay, there is no need to find average atomic mass. But in case of isotopes, since the isotopes are present in different composition, different percentage, we have to find the average of that. Okay, so how do we find average of that? We will take the average atomic mass, we will write the percentage, how much percentage of this isotope with atomic mass 35 plus 25% of atomic mass 37. Okay, so here we have to calculate 35 into 100, 35 plus 25 by 100 into 37. Okay, so if you calculate, you will get 35.5 units. So that's why the average atomic mass of chlorine isotope or chlorine will be 35.5 units. So here if you see, it's calculated same way how I did. So you get average atomic mass of chlorine as 35.5 units. That means, it doesn't mean that there is any single chlorine atom has this. It is nothing but it is average of all the atoms of chlorine, because when you take an atom of chlorine, it is having both the isotopes in that. So we have to find the average atomic mass of chlorine or any other isotopes present. Okay. So here they have given you about certain applications of isotopes. So isotopes has several applications in medical field also. In nuclear energy concept, isotope of uranium. Okay, isotope of uranium is used as a fuel. Okay, in the nuclear reactors, it is used as a fuel and providing energy through controlled nuclear fission reaction. It is used as a fuel in nuclear reactors, which is used to generate electricity. Okay. Cancer treatment also, isotopes of cobalt is used in radiation therapy for cancer patients. Okay, targeting the cancer cells. Okay, targeting the malignant types of cells. And medical also, in medical field, isotopes of iodine is used in the treatment of goiter. Goiter is a vitamin D deficiency disease. Okay, and also thyroid disorders also it is treated using isotopes of iodine. So last concept is about isobars, which is different elements. Okay, they are different elements but they have same mass. Like example, they have given you calcium and argon. Now calcium is atomic number 20 and argon is atomic number 18. But you see their mass number will be 40 and 40. So what will happen? The number of protons are different. Right? The number of protons are different. Their mass number is same, right? Proton here is 20, here proton is 80, but mass number. Now if your neutrons will also differ, right? So they have same mass number but different atomic numbers. So neutron here will be 40 minus 20, that is 20. Here neutron will be 40 minus 80, that is 22. Okay, so here number of neutrons will differ, protons are also different, but the mass numbers are same. Okay.